All right, this video we're going to go through problem number 6.3, which was assigned last week for homework, and so you should be somewhat familiar with it. We're trying to predict the fare of flying on an airplane, and we've got a bunch of data points, including fare, and that's going to be our response variable, and we want to use these predictor variables or explanatory variables to explain that. So the first thing we're asked in part A is to make a histogram and a correlation table and scatter plot matrix for all of these variables. So let's go over here to JUMP, and if you don't have the airfares data already installed or loaded up, which I do, just go up here to File, Open, and then navigate to wherever it is that you've got that. I've already got this in here, so I'll just double click on it. So let's first of all look at the scatter plot matrix. That's the last thing they asked us for part A. But let's look at that first. If you go Graph, scatter plot matrix, all this is going to do is make pairs of variables, scatter plots for the different pairs, and we want all the continuous variables or numerical variables, which are highlighted here. We want those as our x's, so that when we say OK, we get a bunch of scatter plots. And we can look at these things. You can kind of play around with this if you like. Make it a little more user friendly to look at. And what we're looking for here is relationships, linear relationships. You see coupon. As coupon increases, so does the fare. New, high. These other ones don't really give us too much, except for distance looks even better than coupon. So if I had to base it just on the scatter plots, I would say distance has the best relationship with fare. Let's look at the other part of the question that says calculate the correlation matrix, and then we'll finally make the histograms. So we're going to go to Analyze, Multivariate Methods, and then Multivariate. And notice this says pairwise and higher relationships among number of columns. And so we're going to just select all of the numerical variables that we have here. And we'll throw all of those in. And when we say OK, we not only get a correlation matrix, which is what we have up here, but we also get another scatter plot matrix that does all of these things pairwise. And this has quite a bit more scatter plots in it than what we previously found, and that's because it's looking at the pairwise correlation or pairwise scatter plot for all of the variables, where we really only cared about this top row, looking at the scatter plot between fare and the other variables. But let's go and look at the actual values of the correlations. Again, we're interested in fare versus everything else, and so coupon's got a correlation of 0.49, and distance has a correlation of 0.67. So again, that's telling us distance is the best of all of the variables for explaining what's going on with fare. To get the histograms, there's a couple different ways we can do it. We can do it one at a time with the graph builder. We could also do the scatter plots one at a time with graph builder. So drag fare over here and say give us a histogram like that. However, that's not what we're going to do. We're going to instead go click on this button that says distribution, and we're just going to throw all of the numerical variables in here. Say OK, and here we have the histograms for each of these things. And if we want to, we could, instead of having horizontal histograms, we could change those to vertical histograms. But I'm not going to do that at this point. For part B, we want to explore the categorical predictor variables and their effect on fare. So we're going to come back over to our airfares data. We're going to go up here to Analyze, Tabulate, And we're going to put coupon, not coupon, vacation, Southwest, slot, and gate. And drag those over here to the drop zone for rows. We're going to put fare in the drop zone for columns. And then we're going to say n, mean, standard deviation, and we can put anything else that we want here as well. I'm going to drag it over here and put it as sum. And then we're going to look in this table and see which has the biggest differential in mean fare. And it looks like Southwest. For routes that are not covered by Southwest, the average cost is $188. For routes that are covered by Southwest or flown by Southwest, the average fare is $98.38. That turns out to be the biggest differential, so that tells us Southwest is going to be the strongest single categorical variable for predicting the fare. Part C, subpart 1, says to partition the data into training and validation sets. So let's do that. We're going to first create a validation column by coming down here to predictive modeling, make validation column, and we want to do a 60-40 split between training and validation. And we're going to use the seed 1, 2, 3. If you're using JMP Pro 13, this should give you the exact same validation column as what I get. May or may not give you the same as what the solutions are in the posted on Blackboard, because they were generated with JMP Pro 12. So probably they're going to be the same, but no guarantee on that. So we're going to click Fix Random, and we see a validation column that is here. Part C, subpart 2, asks us to use a mixed stepwise regression procedure to reduce the number of variables. So let's go over to JMP to do that. We go to Analyze, Fit Model, and we're going to say fare is our Y variable. Our X variables are everything from coupon down to packs. And we're going to throw that here. And then validation is going to go in validation. And we're going to say give us stepwise regression, and then say run, and brings up this output. And we're going to use mixed, so change that to mixed. We're going to change our criteria to p-value threshold, and then we're going to say go. And we can watch this run all the different models, and finally it stops with this one that has everything, all the variables we put in except for coupon and new. For part 3 of part C, we're asked to repeat what we did in part 2, except for instead of using mixed stepwise, to use exhaustive search over all the models. So we'll come back over here, click on Analyze, Fit Model, and we'll do recall. That throws almost everything back in. Let's get the rest of it. So we'll go packs up to coupon, add all that, and validation is still there, and we're going to go stepwise, and then we say run. And at this point we have the opportunity to do the same thing we did in part 2, but instead we're going to click on this little button, say all possible models, and we want there to be a maximum number of terms of 13, because that's how many predictor variables we're considering. I don't want to output 56, let's just say 10 of the best with each number of variables, and we'll say OK. And here's what we get. All of these values. If we want to compare these things on R-squared, root mean square error, AICC, or BIC, we can just right-click on this and say sort column by. We'll do that in just a second. Instead, first we're going to add in malloc CP, so go to columns and then put in CP. And now we get all of these numbers, and now we're going to sort by malloc CP, and we want to do this ascending, so smaller the better. When we do that, we see the model with 11 x variables is one that has the best malus CP. If we click on this little button right here, it will show us what that model is. And notice it's the same as what we had before. Coupon and new are not in there, and everything else is, although the order is different. That's an artifact of how I put these variables into the function call. If I want to check it out and see which gives me the best model based on AICC, for example, again, I want to do that ascending, and it looks like we get exactly the same model. So according to malus CP and AICC, we get the same best model. If we try root mean square error, also do that ascending, then we get the model with 12 variables that has everything but coupon in it is the best model. So we're going to go ahead and click on this one here, and we can look at the validation and see that the root mean square error in the validation is 35.29 versus 35.93. So that tells us we're not overfitting. Let's compare that to the next best model. For this one, we get 35.21 versus 35.92, which is the same. So the simpler of these models is going to be the one that we want to go with, referencing or calling on Occam's razor for that. For part 4, we're asked to compare the predictive accuracy for the models found in 2 and 3. And since those are the same model, they are going to have the same predictive measures. So nothing else to do on that. Part 5 says, using model 3, predict the average fare on a route with the following characteristics. And here's a bunch of data points. So we're going to go over to Jump Pro and put all those numbers in. Back over here at the output, we have our 11 variable model selected, and we can see that again it's just coupon and new that are not in the model. So if we come up here and click on make model, this will bring up the model that we have specified, and we can just click run, and this gives us the output for the model. Click on this little red triangle and go to save columns and say predicted values. And when I do that, I can now go back over to the original data, and I see a new column called predicted fare. And so I can scroll down to the bottom and I can put in the data values that I would like, and that's going to populate. So instead of making you do this or making you watch me do this, I'm going to push pause, and then you'll see what I get when we come back. So you can see I put all these numbers in except for the last one, 12,782 is the value, and then when I scroll over here, this is supposed to give me a number. And it didn't give me a value because I put in the wrong column here. So let me go back to the model, go back to this triangle. I'm going to right click on it, save columns, and it's prediction formula. I did prediction value before. That's not going to allow me to make predictions going into the future. So I'll change that to formula. And now when I come back over to the data, I see that the fare, the predicted fare, is 252.04. Part 6 asks what the predicted fare would be if Southwest decides to cover this route. To answer that, all we need to do is come down here and change this value right here for Southwest. And you can see all I did was copy the previous line and then change Southwest to yes instead of no. And then let's go over here and see what the outcome is. $212.93 versus $252. Part 7 brings up a good point, and that is that not all of the variables that we have are going to be available to us. They ask us to identify which ones are not going to be available. So let's come up here to list of the variables, and we look through this. New, the number of new carriers entering the route, that's something that we're not going to have. And Southwest, whether Southwest is on the route or not, that's also something that we're not going to have. And then the number of passengers on the route will also be something that we don't know. PAX, number of passengers, and whether Southwest use the route can be estimated by looking at data for similar routes. New, that's maybe something that's a little bit harder to estimate. So part 8 says throwing those variables out, refit the model, and then part 9 says get an estimate for the price, predicted price, using the new model, and part 10 says compare the predictive accuracy of the two models that we've done this for. So let's go ahead and do that. So we're back over here. We're going to go analyze, fit model. If we click the recall button here, it will populate the last model that we used, and looks like I've already taken out PAX, Southwest, and new. I'll show you how to do that real quickly. If I've got new in here and I want to take it out, I can just simply right click on it and say cut, and that will take it out. Okay, so we want to do exhaustive search, so we're going to come in here, click on the little red triangle, say all possible models. Now we only have 10 variables, so we had 13, we took 3 out. We only want to look at the top 10 for each besides the model, and we'll let this run, and then we'll add CP and sort by CP ascending. And when we do that, we see that the best model is the full model, has a malus CP of 11, and if you look at these other AIC and RMSE, those are actually the best as well. So this is going to be the best model. And so let's come up here and let's say make model. This is going to fit the model that we have. And once we have that, we can come to the little red triangle, say save columns, prediction formula this time, values. And that column is added to our data set. Notice that the fares are already put in there. 237 is the predicted price. Now this is the same regardless of whether Southwest is in the model or not in the model, or actually whether we say Southwest is yes or no, because Southwest is not in the model. Neither is new, and neither is PAX. So we could take those values out if we like, or just leave them in, doesn't matter. And just get rid of this one. And you see that the first model prediction goes away, but the second one stays the same. So let's undo that, and we see that we have 237 versus 252, or 212. Now we're asked to compare the predictive accuracy of these two models, and that means we're going to look at the validation data. For the first model, we have root mean square error for the validation set of 35.26, and for the second model, we have a value of 40.76. And so does that make sense? Yeah, it does, because what we're saying is we have less information in the smaller model, so there's going to be a bigger error. And it makes sense to reevaluate the model once that other information becomes available.